As we near the halfway point for this course, we're going to look at the unit step and unit impulse functions. Now, to understand why these functions are important or how they can be used, we want to recall an RC circuit or an RL circuit. So we can simply say that the current for the capacitor is equal to the current for the resistor. So if we have a node between the capacitor and the resistor, we simply set up a KCL as follows. And we're going to use the fact that the displacement current for capacitor is equal to the capacitance times the time derivative of the voltage over the capacitor. Or in our case, VC is equal to V, which is also going to be equal to the voltage over the resistor. So we can plug this in to the second equation here, and we can integrate and arrange things such that we have this function. Now from this, we simply say that the natural log of the voltage is equal to minus T divided by RC plus some constant C1. This constant C1 is not related to this capacitor value. It's just the constant of integration. So from that, we manipulate this equation to say that the voltage is equal to E to the minus T divided by RC multiplied by E to the C1, where E raised to the C1 is going to be equal to V naught, or our amplitude that comes with this exponential. And we can find that the current through the resistor is simply equal to V naught divided by R, and then we get this exponential that comes for the ride. And we had a time constant, tau, which was equal to the product of the resistor times the capacitor. And we can do a similar procedure for an RL circuit, but we can skip that for now. What we really want to remember is how to work with the displacement current for a capacitor and the voltage over an inductor, and how we had these derivative relationships in the time domain. That's where our focus is going to shift to. And we also had circuits that look like the following, where we have an RC circuit, but we had some switch where it closed at time equals 0. And this is fine, but we want to represent our voltage source and this switch as a function. And what we're going to do is represent it as the voltage that we had times this unit step function, and that's denoted by U because it varies in t, it's a function of time. And this is a common function. We'll use this throughout many of the courses, but I believe this is the first introduction of it. So we want to define this unit step function such that at times t less than 0, the value is equal to 0, and at times after 0, the unit step function is equal to 1. So if we plot that on a graph with respect to time, we can see that at t equals 0, we sharply shoot up to 1. And we can shift this function by some t naught, such that our unit step function becomes 0 for t less than t naught, and then 1 after t equals t naught. But if we look at this shifted unit step function, we simply see that the limit, if we come from the right-hand side or the left-hand side, it gives you different values. So it's not really defined at t equals t naught or t equals 0 for the case that we initially looked at. Now, if we integrate that step function where it's shifted over the interval minus infinity to infinity, we know that after t naught, that value is going to be equal to 1. So we can swap the limits for the integrals, and then we just have a 1 inside the integral. And that's how we can do that integration. Now, what about the derivative of the unit step function? Well, there's not really a nice way as compared to something if we had the time derivative of t to the n. So we're going to go back to the original formula for a derivative. So we have the limit as h goes to 0 of u of t plus h minus u of t divided by h. And we kind of just want to look at what that derivative looks like. So in the blue here, we're going to have the unit step function that's not shifted, and in the red, we have the unit step function that is shifted. So we have this overlap here that's maybe a little bit difficult to see. So the shift occurs at minus h, and these two are the functions that we have in this derivative equation. Now, if we subtract them as the numerator of the derivative equation calls out, we simply get something that looks like this. And again, it's just the subtraction of this function with this function. So now we know what the numerator of that derivative looks like. And we want to simply just state a scaling factor. So if we have some constant a times the unit step function, it just scales it by a. Pretty simple, but we're going to need it for the next step. And this is where we want to look at the derivative formula without the limit in there for right now. And it will look like this graph on the right, where we have some amplitude 1 over h. So we know what essentially everything of that derivative looks like aside from pushing that limit h to 0. But if we actually push h to 0, the width of this block pulse simply goes to 0, but the amplitude tends towards infinity. So if we keep getting closer and closer and closer and closer to 0, we get this extremely thin rectangle. And as that limit tends towards 0, we get this new function. And this new function is the derivative of the unit step function, and we call it the delta function. Now we denote it by this delta here, and it is defined as 0 for t less than 0, infinity at t equals 0, and 0 for t greater than 0. So it's kind of weird, but both of these functions are useful in what we're going to be doing in the near future. So getting back into circuits, we want to consider the RC circuit where we had that switch. We're going to represent that as this unit step function. So if we do a KVL around this loop, simply say that the input voltage minus the voltage over the resistor minus the voltage over the capacitor is equal to 0. We know that the current for the resistor is going to be equal to that displacement current for the capacitor, which we know we have a relation like this. So we can express this function like this, which by a little bit of manipulation and algebraic modification, we can have this last equation down here. Now this differential equation isn't too bad to solve. If the voltage is a nice function, we can work our way around it in the time domain. But let's consider an RLC circuit where our KVL looks like this. Or we can modify that to arrive at this differential equation. Now in this differential equation, we have this voltage, which is our voltage source. And if that voltage source is equal to some Vs times a unit step function, well, the derivative gets us some delta function. But we have solutions, and that's when we start to get out of the time domain and get into the complex frequency domain.